As Akhil said, this is probably the third consecutive panel that you are attending, and therefore I understand that there must be some fatigue, but we promise to make this worth your time, or we will scare you sufficiently to remain seated for the next 45 minutes or so. But we have an extraordinary panel of people whose frighteningly impressive resumes I am not going to read out. You can take a look at the booklet and understand if, for instance, after the panel, if you have some questions that you'd like to take to them. Wendell, for instance, has already done a speed talk, so I'm guessing you've had a chance to talk with him. But our really extraordinary individuals who've been working on some fascinating things I hope they will share with you today about. And the objective of this panel is to really extract some of the reasons why we've, for lack of a better word, why we see the human body as an incubator for new technologies, and why it is so contentious that technology, that the human body is today the site of technological intervention, although this process has been going on for a while. And to highlight the fact, as some of us were discussing before we came into the main hall, that you have a process that concerns itself with the development of ethics in technology, and you also have an equally autonomous process that relates to the development of bioethics or ethics that are used in, for instance, the medical profession. To what extent is there some convergence between both, which is fairly essential to having this ongoing debate and continued innovation of technology as it relates to the human body? Or if it is not compatible, or if these two sets of autonomous principles are not compatible with each other at all, then what does it mean for the growth of biotechnology as a sector as a whole? So let me start with Manuela and then move from that side to Wendell. Manuela, I'm just going to request all of you to speak for 4 to 5 minutes, and then let's open it out to questions, and then perhaps have a conversation with each other about the various points that you've raised in your introductory remarks. Yeah, over to you.
Okay, thank you so much. I felt the responsibility to talk about these important themes. So the themes of biotechnologies divide and security, for me, that could bring negative consequences even in healthcare system, like design of biotechnologies or new biomedical technologies for diagnosis and services in general, including the information system and a clinical engineering field. So in my experience in a public hospital and in a big companies should be aware of the possible impact. So, but the impact must be positive in an equitable way. Today, I considering in my work three important factors are equality, equity, and safety. For me, it is necessary to considering as these three factors as a minimum criteria to working in a multidisciplinary team. So usually I talking a lot with the physician to understand what they need. So I think that, for example, to implement the standards for biotechnologies in general or for health technology assessment, bioengineers and bioethicists can be considered as references, new professionals to perform this function. And in one hand, a biotechnologies divide having a progress advances in biomedical field and in biomedical medicine. So in the other hand, there are an imbalance for access to the cure for all people. So in general, the bioethics became for me essential in science because when talking about a genetics test or a genomic test for oncological field, for example, or for a rare disease or euthanasia, it is necessary to considering the solution in the best solution in the term of care of the patients, of patient centricity, because the patient there are there are the most actor for processing in healthcare. Thank you.
All right, thank you very much. And I'm gonna start by clarifying. So this morning I was in a panel where we were discussing trust in AI. And I currently work for IBM, but before joining IBM, I was a cancer researcher. And the work that I did was actually in trying to develop targeted therapeutics for cancer. And that kind of work requires a lot of understanding of and applications of biotechnology. And that's what I wanted to focus my remarks on the potential benefits of biotechnology, particularly in research. So one of the things that I constantly had to do was to test out the different drugs and imaging agents that we were testing on rodents. And for us to make that test possible, we're actually using transgenic mice, or what we call in science knockout nude mice, which basically you remove some aspects of their genetics so that you're able to develop cancer in them, but also to test them. And as we talk about biotechnology and the ethics of it, I think one of my perspectives is particularly in understanding or appreciating the level to which that level of genetic editing, if you call it that, has led to significant advances in medicine, particularly for human beings. If you're talking about cancer research, if you're looking at many drugs that today we're calling monoclonal antibodies, are being developed in genetically modified animals. And so that's the perspective I take, where I see very clear benefits in the use of biotechnology to drive human progress. But even in taking that perspective, one of the things that I am especially cognizant of as a scientist is the fact that we have a lot of responsibility in being able to develop biotechnologies for the right purposes as humans or as scientists. Two, in being able to clearly test out the potential impact of, technologies that perhaps result in genetic modification. And then I think we also have, the onus is on us as scientists to be able to articulate these topics in a way that non-scientists can understand, so that we're able to have debates that will result in biotechnology being driven by our collective value system. So that's my perspective. And the last point maybe I will make is we haven't even talked about the importance of biotechnology in driving other industries such as agriculture. And there's been quite a lot of discussion, particularly around how those advances may be able to impact particularly our continent and others where there's food security is such a topic. And so I think it's just so important for us to be able to make sure that we have the right people at the table to be able to have those discussions, and who can understand what it means, what the potential uncertainties in addition to the challenges, so that way we can walk the path and make decisions not out of fear, but out of understanding.
Thank you.
Sorry.
Is that working now? Okay. Thank you, Arun, for opening the panel, and thank you all for being here. My name is Shinjini Kundu. I'm a physician currently at the University of Pittsburgh Medical Center, and I'll be shifting to the Johns Hopkins Hospital next month. Now, before I became a medical doctor, I actually did all of my training, education in engineering. I have a bachelor's, master's, and a PhD in engineering. And one of my areas of research is artificial intelligence for detection of diseases from medical images that humans may not be able to detect. Now, the reason why this became an area of interest of mine is because medical images are one of the fastest growing sources of medical data. And let me ask you in the room, how many of you have had either an X-ray, a CAT scan, an MRI, a CT, any kind of medical image taken at some point. Usually when I ask this question, almost all the hands in the room go up, if not all of them. And that kind of represents kind of the widespread use and the sort of the underpinning of medical diagnosis in medical imaging in every field of medicine. Now, in medicine, there's been a lot of progress in treatment of diseases, but there has not been so much progress in sort of prevention of diseases, and how do we prevent diseases from occurring in the first place? And that kind of requires an understanding of how can we detect diseases at an early stage when there aren't a lot of signs or symptoms, and there aren't observable cues on these imaging studies. So what I did in my work is that I developed a new technology called transport-based morphometry. I call it TBM for short. And basically, I use TBM to try to mine medical images to find evidence of diseases that might be imperceptible to humans. And initially, we didn't know how widespread these sort of imperceptible signs of diseases are, but what I found in my research is that in a lot of different diseases, there are very early cues in medical images that are present, maybe years before the development of the disease, but humans just can't detect them. Now, for example, one of the kind of projects I worked on was early detection of osteoarthritis, where we had patients who were completely healthy, had no signs of symptoms of disease. We looked at images of the knee cartilage, and based on these images, even, there's nothing even visually evident to doctors on these scans either. But using the technology I developed, we were able to find that those images contained clues that allowed us to detect with high accuracy who will develop osteoarthritis later, 3 years in the future, who's going to develop signs, symptoms of disease. And that was kind of a breakthrough for imperceptible information. Now, the other piece of that is how do we trust sort of our AI technologies, and how do we actually build a partnership between what an AI-based system is telling us and what we as humans who are doctors who might be trained in biology understand about the human body? Like, how do you reconcile the two pieces? So part of this TBM technology that I developed is that it allows us to open up the black box when it comes to using machine learning. So anything that machine learns, machine logic, can sort of be mapped back to medical images in a form that humans can visually interpret. So it allows previously imperceptible information to become perceptible. And I think that closes the loop between humans and sort of the AI side and technology side of things. So I'm really interested in that interplay between artificial intelligence, between new emergent technologies in the computer science fields, as coupling that with medical diagnosis and the care of patients. And I do agree that it raises a set of interesting questions, because we go from a field that's highly regulated, healthcare, which is regulated in the United States, at least in every possible way, from many different angles, from insurance companies to pharmacy, to there's a legal aspect, there's an ethical aspect, to a space in artificial intelligence, which is relatively completely unregulated. It's kind of the antithesis at this point. So reconciling those two aspects is interesting to me. And that's what hopefully we'll be exploring a little bit more today.
Well, thank you very much. Just as this last example shows, the various researches, the various benefits that we can get from biotechnologies, they're really vast. Oftentimes people just think in terms of genomic research, but here's an example of something that relies very heavily on artificial intelligence, and at least is not necessarily indicative of anything that we might find within genomics, though it's possible that some of the features being revealed are. I'm going to stick to the gene side of the discussion, but I want to say, even when we're talking about genomics, there are thousands of different techniques, tools, and research trajectories underway. And let me just flag a few of them, because each of them has their own ethical considerations, and the deeper you dig, the ethical considerations become more and more complex. So on one level, it might be argued that anything that improves people's health prognosis is beneficial. But on another hand, we have some very simplistic arguments about playing God, for example, when you're altering the human genome. And yet there have become certain fields of research, such as pre-implantation therapy, where if one of the parents is carrying a genetic disease, we find it totally acceptable to review various situations where a sperm has fertilized an egg, and pick out the case where we have a sperm and an egg that don't carry that genetic defect, and then pre-implant that for the child. In a certain sense, we're saying that there is a benefit here that the child does not carry the genetic disease. So we find that kind of research acceptable. But we find it unacceptable, or we have these charges such as playing God, if a parent decides, for example, that one of them's very tall and the other's very short, and they want a tall boy because they're hopeful that he will be an excellent basketball player and make millions of dollars in the NBA. Is that such a serious decision to make? Is it playing God? Is there something incorrect about the parents placing their aspirations on their expected child? Some people argue yes, some people will argue no. But is it so natural, or is it God-given, or do we surrender to God the right to determine that when a random sperm finds its way to fertilize an egg, that is God's will, particularly if it might carry a genetic disease? So again, these become very simplistic arguments that we get involved in that direct us to be for or against different kinds of gene therapies. Now, we are moving into a world where the gene therapies available are vast, not just for human health or altering the human genome, but also for tweaking genes that may be causing diseases right now in our body and trying to reverse that, or to create totally new genes that we introduce into an organism. And the organisms are not just human organisms. In fact, the human organisms tend to be the last bastion of our research. Very few times is the first level of research on human organisms. More likely, it's in one of two forms. It's using animals as subjects, the notorious lab rats or lab mice that are used everywhere, or it is the creation of totally new biological products through what we call synthetic biology. This is really using genetic research to create biological products or new organisms for all kinds of purposes. In some cases, the purpose might be to bring back an organism that is extinct. Is that good or is it bad? And does it depend upon which organism you want to bring back? Or in other cases, we have what are called gene drives, which is the capacity to cause an extinction in an organism we want to get rid of. So we have two different species of mosquitoes that are carrying yellow fever, dengue, and malaria. No one of those species carries all three of those. But the point is, we now have in the laboratory genetically altered mosquitoes that do not carry the gene. We also have techniques for introducing those organisms into the wild, where after a few generations, and when you think about reproduction in insects, it's very quick. After just a few generations, we could eliminate all the mosquitoes that carry malaria. Wouldn't that be a wonderful boon for Africa? It would, wouldn't it? But now think of somebody altering a different species that they introduce, and it actually devastates some of your most prized environments because it causes a collapse in the ecosystem in that environment. Do you want to see those species released? So these are the kinds of ethical dilemmas we are now entering into, and it's not merely what we want or what we think is right or wrong, but it's also what we can effectively control. Thank you.
Excellent. Let me sort of take off from where Wendell stopped, and that is on the idea of playing God, and provoke all of you into thinking about the politics, or at least holding forth on the political dimensions of this debate, because I refuse to believe that the development of bioethical principles are somehow devoid of a political context under which we are all operating. When the Human Genome Project was conceived by a group of advanced economies in the early 90s. I mean, they started thinking about it in universities, in American universities and European universities in the late 80s, and of course it came into fruition, I believe, in 1991. The mood among the scientific community was largely one of awe, of the fact that they were truly and genuinely on the verge of scientific breakthrough. In fact, I think one of the people who were behind the Human Genome Project in, I don't know, it was one of the West Coast universities, said that this was the ultimate quest for the Holy Grail. And if one aspect of one reaction to the Human Genome Project in the 90s was defined by awe, the reaction to it was, again, people were incredulous that the human genome could finally be, decoded. The New York Times at that point called it an attempt by third graders to read Kierkegaard, right? So at that point, it was the complexity of the exercise that really bewildered the community of scientists and lay people who wanted to, understand more about biotechnology. Today, given the ubiquity of technology, we have a debate on ethics. And I'm wondering, and I want to sort of provoke you into thinking, as to whether it is the pervasiveness of technology that is generating this debate on ethics. Why is it that we did not have the same kind of debates when we talked about the Human Genome Project as we do when we hear about a doctor or a scientist from China using CRISPR to perform gene editing of babies? I believe there is a certain politics to it. I think that there is a certain, like I said, the fact that technology has become all too readily available that are scaring certain centers of knowledge production and consumption into believing that it is now time for ethics. And ethics then becomes a way of curtailing the advancement of technology and the advancement of societies in certain parts of the world. I don't know whether you guys would agree with this. I mean, I think you would all agree the fact that the availability or the ease with which you can now splice genes and the advancements that have been made in recombinant DNA technology is certainly what is spurring this debate forward. Does the fact that this debate on ethics is now so prominent, given that anybody relatively can have access to this technology, does that fact worry you? And I want to start with Wendell.
I have met a man who said that his son has used CRISPR-Cas9, this new technology that came along a few years ago to speed up our ability to edit a genome, to actually replace certain segments of the genome with other genes. He said his high school son has done it. Now, his high school son probably did it with some aid, but there are tons of graduate students who do it. MIT has a big summer camp, in effect, every year, where it brings in teams from all over the world, and they do synthetic biology. They create new biological products. One team would create, let's say, a plant that glowed in the dark, just to give you an example of one of the things they did. They do this every year. So on one level, it seems that gene editing is becoming very easy. It has an aspect almost like tinkering with radios were 50 years ago and assembling your own computers out of components now. Except that to do anything really sophisticated is not easy. And that's sometimes missed in all this discussion. So the actual gene editing isn't so hard, but getting a particular result can be very hard. So one of the things we forget is that when the Human Genome Project was started, the expectation was that there would be a discovery of somewhere between 100,000 and 200,000 genes. And that meant that many features of a human, for example, or an animal, because by and large, most mammalian species carry 97% of the same genes. It's only 3% that distinguishes us from other animals, that every feature would be gene-specific. Well, the reality was there are not 100 to 200,000 genes. They uncovered 20 to 25,000 genes. That actually was bad news. That would make you think it was less complicated. But what it actually means is that every feature that develops may actually develop out of many gene interactions, and we don't understand those gene actions. Furthermore, there are complexities in genetics where environmental factors can turn genes on and off. And the environmental factors can be very much the conditions within the cell that the gene is, not to mention, radiation coming from the sun or something else that can cause an effect. So we're actually moving into a world of great complexity and a world where it's going to be a lot harder than was originally presumed to, for example, prescribe 12 features that you want your baby to have and be able to have that designer baby. That's unlikely to happen in any time in the near future and probably should be heavily restricted, because what happens if you produce mongoloid children or chimeras or other conditions where the child actually has a genetic disease or a genetic circumstance? So I don't know if that quite got at your question, but that's the foundation of the territory we are moving into. And it gets us, I think, to the geopolitics in the sense that a lot of these attitudes are just simplistic attitudes that different communities have. So the prohibition around engineering the human genome, that was promoted by the administration of George W. Bush, who was very much under the sway of his conservative constituency. And there was deep divisions around it in America. But there is a kind of yuck factor. There is a discomfort we all feel about editing the human genome, and therefore it is something people do respond against. But the reality is, in research laboratories around the world, they are actually editing the human genome. It's only in this one case in China that has been done in a context where the children were brought to birth.
I just want to push on that. Am I really naive to believe that were we to have heard the news of the gene editing in babies from a research group in MIT, the world would have received it very differently from the news of gene editing having happened by a doctor in China? I mean, is it really naive of me to believe that the world would have received it very differently? Because I don't think that the production of knowledge...
There is a knee-jerk reaction, particularly coming out of America about China. And particularly right now, since we have an administration who has raised the tensions between China and the US. But I think the actual creation of living babies through gene editing in anything other than something like pre-implantation therapy would have created a reaction, even in MIT. The fact is we know of tons of human gene editing going on in research laboratories in England and elsewhere. That actually created quite a bit of a fervor too. But that was not research around bringing babies to life. So at this point, there is at least a tacit moral. There's never been an absolute legal prohibition, but there is a tacit moral prohibition on editing the human genome. But, and it has a geopolitics around why it exists, but yes, we do need a full and deeper discussion about when it may or may not be acceptable to do so. The reality is China will not be the first incidence. We saw what turned out to be a fraud in Korea years ago, and even though South Korea went along with the prohibition, they were actually thrilled with this fraudster scientist until it became clear that he was a fraud.
Well, I have some thoughts about kind of why gene editing might be received differently in different communities. First of all, Siddhartha Mukherjee said that genes are the line between biology and destiny. And we've seen that in studies of twins, identical twins, who are reared in different environments and different households, who are raised differently. They actually, as adults, share a lot of common similarities, a lot of common behaviors. They share tastes in music and food, and the similarities are much more than you would expect just from random chance. And I think all this evidence points to the fact that human behavior is strongly influenced by genes. Now, that said, the correspondence between genes and behavior is much, much more complex than we initially thought. And we're talking hypothetically about scientists in China, but that's a real case that there was a scientist in China, and back in November, I'm sure some of you saw the news, that he edited human embryo, and he basically created a set of twin girls who were resistant to the HIV virus by editing a couple genes in the embryo. And so these babies they're born, healthy to mother. They're living in China somewhere. But he came under, there's a lot of controversy around that. But one of the kind of controversies is, at an individual level, is that when you're editing genes, because these genes affect biologic behavior in such complex ways, there's a lot of criticism that he might have been tinkering with other pathways that are poorly understood. So right after that, there were reports from doctors in Spain that he may have actually rendered these babies more susceptible to the flu. There are reports that editing this gene was associated with a shorter lifespan, and the list goes on about the possible sort of harms incurred to these babies as a result of editing the genome to make them resistant to the HIV virus. So,
Shinjini, let me stop you there and ask you on the subject of tinkering, because Wendell brought it up, right? And he sort of lightly, in a lighter way, and he compared it to the equivalent of tinkering with radios, in terms of. But an entire generation in the United States, for instance, in Silicon Valley, was raised on a culture that tinkering is all right. And tinkering is fine, and it doesn't necessarily have to do with Silicon Valley alone, where, the culture of the garage and the innovation in the garage was privileged. And it was considered, people who failed and people who innovated under very constrained economic conditions were, voted as a badge of pride. And that is, in fact, the ethos that still drives innovation in Silicon Valley. Why is it any different with human beings? And I'm not asking it in a, to be an extremely provocative way, in the same way that man has sent to space. Right. There were people who tested, folks, their own anatomical and biological limits by sending themselves to space, and there were programs that were sanctioned for that explicit purpose. I am finding it difficult to understand that, sure, there is complexity in this debate, and of course the doctor in China should have understood that complexity before, going ahead and editing the genes of these babies. But how is that any different from the way mankind has approached innovation in other areas of technology?
Well, I think that there are a few important differences. One is that if we're editing genes selectively of humans, that necessarily means that some humans will be better than others. And if we think about sort of the institutions that our progenitors have rejected in the past, racism, sexism, homophobia, casteism, elitism, if we think about those institutions, and if we think about human behavior, then we must draw a line where we stop tinkering at the point at which we're choosing to have a boy child versus a girl child, or to have a child with light skin versus dark skin, or to have a child who is heterosexual over homosexual. And I think these kinds of choices might make people uncomfortable because if we make the wrong sort of selections, or I guess depending on our genetic selections, we are embedding another generation of possible injustice and possible biases against.
But haven't we already done this? And it's not just the bad guys who did it during the Second World War. For instance, the Eugenics program in Sweden, which was, so it's not as if folks who have, there have been folks well embedded in the liberal international order who have been trying to do the same things. And why is it that when there is a challenger, politically speaking, and when there is an innovation that the challenger presents, why do we suddenly introduce complexity as some sort of as an obstacle to that sort of innovation? Perhaps I'm being naive, but I feel that there is some complexity to the debate about complexity.
I agree. There's some complexity to debate about complexity, and I think I can tell you a story that kind of highlights the precedents that we have about biology and fairness. And I can tell you the story about, there's the South African Olympic runner. Her name is Caster Semenya. She's 28 years old, naturally born female, but it turned out that her testosterone level was higher than the cutoff to be able to participate as a woman in the race. And this is naturally occurring. She wasn't taking any supplements. It just so happened that her testosterone level was higher. But it's known that testosterone can sort of influence performance. It influences muscle strength, it influences endurance, and it's known that that's why men can have faster sort of race times than women. Testosterone is known to influence performance in that way. And even though it was controversial, she was ultimately banned from participating in the race as a woman. Now, if we look at this case, why was it that it was so controversial? One of the sort of principles that we can apply is that the principle of biology and fairness, that some humans are born with certain natural advantages, but as a society it makes us uncomfortable to think that some humans could be inherently better than others, whether that's naturally occurring or whether that's artificial. Now, if you bring sort of artificial engineering into the debate here, I think that humans, we have an inherent discomfort with the idea of creating a genetically superior subspecies or a species of humans that have certain advantages to be better and stronger and more robust to diseases over others. So I think it's the question of fairness and an equitable sort of distribution and access to these technologies that plays a role, at least in some of the discomfort and hesitance over innovation, and just like in any other sphere.
Chatty, do you want to weigh in on this?
Very fascinating discussion. Just to build on to what the two of them have said, I think there's a certain value and perception we as a society have on humans, the human life, and the extent to which we can experiment with it. And I think that plays a significant role in us having a certain level of comfort to discuss things such as genetic editing, where there's so much complexity, as we've said, where there's so much unknown about the possibly unintended consequences. And so I think a huge part of it as humans is just that level of discomfort. It's shown in many other aspects of life. When you talk about, when drug discoverers, synthesize drugs, it's the reason why we start with, rodents, and then maybe we get to high-level animals way before we ever get into testing, in humans. And so I think a huge part of it is just our individual or societal discomfort with what it means to be human, and what, I think we all watch a lot of sci-fi movies, so a lot of what could possibly be on the basis of effects of genetic editing. Now, of course, I think that there's a lot that could be talked about based on how you describe the particular use case. So when we position genetic editing as, we want to make sure that we can take out the specific genes, once we know them, responsible for sickle cell or for, malaria, as you talked about, then it's incredibly positive, and it represents or shows us the potential that can do. The other side is when we talk about all of the unintended consequences. So I think that's the challenge for us as human beings. And to figure out, even when you talk about those unintended consequences, the fact that there's a time scale that we might not be able to predict. Are the effects going to show up in 2 months, in 6 months, in 10 years, in an entire generation? We're not quite sure. So I think that's where a lot of the moral debate also comes through. Yeah.
Okay. As a bioengineers and from biomedical world, the focus for genetic editing is specifically for security and safety, because it is so important during designing of medical machine for in vitro diagnosis to select a final users, select a context to put this medical machine in this hospital. So in Europe, this topic is very important because in according to the certification for in vitro diagnostic, the state members are experiencing a transition period that will last 3 years. So in fact, from 2020, producer changed the process to certification of these medical devices. And this is important because we'll no longer be able to self-certify the medical devices. So we need it through notified bodies. This is a new interaction from companies and a new regulatory system. It is so important for safety for manufacturers and patients then. So the new regulatory having 3 main goals. The first is about increasing protection level on health and security aspects for patients. Before I mentioned the bioethics aspects, so it was not enough because this is necessary to increase the new regulatory for manufacturers. So the second goals concern to free permission, free circulation in Europe, and taking advantage to collaborate from manufacturers in all Europe. And I hope to increase the level of interaction from manufacturers in the world, because it's so important. And the third goals that I read about it is about concern to increasing data transparency, especially for clinical evidence, because it is necessary to analyze data in a correct way, or select the type of data for a specific treatments or for in a specific context. Thank you.
There's a lot going on in these debates, and I've been in them now for about 20 years in a pretty active way. I've heard arguments from those sometimes called transhumanists, who would like to open the door to gene editing, to nanotech in the body, to cognitive enhancements, to all kinds of things that will exacerbate inequalities, presuming that they work, presuming that we get successful techniques. And they have some wonderful arguments about why humanity should be on a path to transcend its limitations. And they have some actually pretty wonderful critiques of a lot of the arguments that conservatives and those who are concerned about the exacerbation of inequalities put forward. And I've heard the exact opposite. In other words, this debate is going on in a rigorous way, and it's not likely to be solved anytime soon, and it's likely to be treated very differently from society to society. In fact, it raises an interesting question about some African countries, because they are seen as open for business by rich entrepreneurs who would like to engage in this kind of research and feel that the barriers to doing that research are lower. Though there have been certain standards, such as in human research ethics, which have now pervaded Africa and South America and poor countries in Asia over the last decade or so. But those are not powerful barriers, though those are potentially strong barriers to doing the research. But what happens when a super rich biotech company comes to your country and they say, we will do whatever. You know, we will build 20 first-rate hospitals if you will only let us do our research. Will you say no? Well, a lot of your countries are already saying yes to Google and Facebook when they say, we will give you all the IT infrastructure you need, but we own the data that goes through these networks, without any understanding that what you're getting probably has a much lower value than what you've traded away. So the fact is, we're moving into this very difficult universe. And whether it's good news or bad news depends upon what your situation is. If you're desperate for a cure to a genetic disease, it's bad news to have anything that slows down the research. On the other hand, we do have research ethics. Research ethics are going to demand that anything that produces a living child protects that child from the likelihood of pain from the research, which actually rules out a lot of gene tinkering, because we have no idea what it means to play around with 7 or 8 or 10 genes in the genome at a time. Furthermore, we raise this question about the trade-offs. So sometimes you may actually alter a gene that solves HIV, but it may actually make you vulnerable to other diseases. Is that a trade-off that's worth it? In many of our cases, we have strengths that actually come together with our weaknesses, but we don't really understand the genetic relationship between those strengths and weaknesses. Eugenics. Well, eugenics looked like a wonderful idea. That's kind of cultivated breeding or selective breeding. That looked like a wonderful idea to countries all over the world before we got into World War II and the kind of selective eugenics of Adolf Hitler. And suddenly eugenics is a bad thing. And yet all of us practice passive eugenics in the sense that we're very selective about who we marry. We ensure that if we have the money, that our children have all the benefits we can give them. So just nutrition alone, as you all know, can be the determinant between having a vital life and having a really horrible life. So we are moving into this morass of ethical challenges and geopolitical issues and politics within different countries and needs and the desire of those who have wealth or would just like to live forever, because that's another thing out there that's pushing some of this genetic research. At the same time, as most of this research is helping us cure diseases that are killing us, will help us with food security, even if we are afraid of genetically modified foods. On and on and on. The trade-offs are mind-boggling.
All right, I think that's all the time we have for the panel. I wish we had some time to take for audience questions, but Trisha has been telling me that we are out of time. But thank you to the panelists. Please join me in putting a hand together for the panelists.